Hello, my name is Dr. Dan Wedding, and this is DrWedding, VB09, for loops and the Fibonacci sequence. Just like many other languages, Visual Basic has two main types of loops. They are the for loop and the do loop. In Visual Basic, there is only one type of for loop, and there are four variations of the do loop. All of the loop types are shown below. For loops, sometimes called for next loops, will repeat a piece of code a fixed number of times. For loops are used when you know or will know how many times the loop needs to execute. Do loops are used when you are waiting for something to happen and there's no way to know how many times the loop will run or how long you will be waiting. To allow more time to focus in on programming examples, this video will only cover the for loop. The next video, VB10, will cover the for do loop variations. This video will demonstrate how to generate a Fibonacci sequence. A Fibonacci sequence is often used to demonstrate a for loop. There are two ways this sequence can be generated. One method uses standard variables, and a second way uses an array. The method that will be discussed in this program will use regular variables that have already been covered. This video series has not covered arrays yet. An array is a data structure that allows a program to access a list of variables that are similar. You can think of it as a variable that can hold more than one value. This series covers arrays in a future video. In the array video, the Fibonacci sequence will be rewritten using arrays. For loops start with the word for and end with the word next. The for statement at the top of the loop will determine how many times the loop will run. A variable, called the loop index, controls how the loop runs. The for statement has three parts that determine how the loop runs: the start value, the stop value, and the step size. An example of a for loop that runs 5 times is shown below. In this example, the loop index is the variable I, but it could have been any variable name. Because there are so many examples using the index I, some beginning programmers think a loop index must be I, but that is not true. The loop index may or may not be used inside the loop. It just depends on what the program requires. In this example, the loop index is inside of the loop and is being printed to a text box. Many times the loop index is I, J, K, L, M, and N. This is a throwback to a computer programming language from the 1960s called Fortran. In Fortran, if a variable started with I through N, the first 2 letters of integer, it did not need to be declared and it was assumed to be an integer. Many programmers did not declare their loop indexes, and they just used I, J, K, L, M, and N. As these programmers moved into C, C++, VB, wrote textbooks, taught in colleges, and made YouTube videos, they carried this habit with them. The students of these teachers also picked up on the habit and carried on the tradition. That is why you will see loop index I in so many examples. It is a tradition that is more than 60 years old and stems from the language Fortran. The loop index I is assigned as 0 when the for statement is executed. This happens at the start of the for loop and happens once. The loop index is then compared to the stopping value. In this example, the stopping value is 4. When the loop index is counting up and the loop index is less than or equal to the stopping value, the loop will run. If not, the loop will stop and the program will continue after the next. When the index is counting down, and the loop index is greater than or equal to the stopping value, the loop will run. If not, the loop will stop and the program will continue after the next. If the loop starts, it will execute all of the commands between the 4 and the next. In this example, it is a single line that will print some information to a text box, but it could be any number of lines of code. When the program reaches the next, it returns to the for statement. The loop index is incremented or decremented by the step size. In this example, I starts at 0 and is incremented to 1. The new loop index is compared to the stop condition. In this example, 4. The loop will either continue to loop or stop. If the step size is 1, it can be left off and the program will assume it is 1. The loop index after the next is also optional. It is helpful to keep the code straight in your head, especially if you have loops inside of loops. But it works with or without it. Now let's do some examples with a loop and write a Fibonacci sequence. I have already opened up a new project named VB09. I have also created a form. The form has 2 group boxes on it. We'll be working with the top group box first. The top group box only has a button and a text box on it. This will be used so we can test various for loops. Here's the first for loop we're going to test. When the button is pressed, text will be written to the text box that says for loop tests. Next, the for loop will execute. The loop index I will be assigned to 5. 5 is less than or equal to 10, so the loop will execute. When the loop runs, it will print the loop index I is, followed by the current value of I. When the loop finishes, the loop index will be increased by the step size of 1. The 5 will go to 6. 6 is less than or equal to 10, so the loop will run again. This pattern will repeat for I equaling 7, 8, 9, 10, and then 11. However, 11 is greater than 10, so the loop will stop running and pick up after the next. Then test complete will be printed to the text box. Let's see this run. You may have noticed that I is not declared in the program. Visual Basic allows you to create a variable that's only used for the for loop. It doesn't exist outside of the for loop. If I tried to print I after the next, I would get an error. You can see that now that I did try to print I am getting an error. The red squiggly line under the I. I won't be able to run this program. If I want to use I in more locations than just the for loop, then I'm going to actually have to declare it. I'll make I a global integer. Once the variable is declared, I can actually print it out after the loop. The error has now gone away. Let's run the program now and see what I is after the loop. I is 11 because that was the condition that made the loop stop running. Let's alter this for loop. We'll change the step size to 2 and see what happens. The loop started at 5, was incremented by 2 this time. As expected, the numbers went 5, 7, 9, and again failed at 11. Let's try one more step size. This time we're going to make the step size -2. This will cause the loop to not run at all. Because the step size is negative, The computer is expecting the numbers to count down. And when it sees that 5 is less than 10, it believes the loop has already completed its task and won't run. If we actually want a loop to count down, we just have to make the starting condition larger than the stopping condition. As always, the loop index starts at the starting value, in this case 20. It will move towards the stopping condition, in this case 10, being incremented or decremented by the step size, in this case -2. When the loop index goes beyond the stopping condition, the loop will stop. The index of a loop is not restricted to being an integer. I've changed I to be a double, and I've changed the step size to 2.5. Let's see what happens when this runs. The loop starts at -5 and is incremented by 2.5 this time. These examples should have given you a good idea of how the for loop works. At this point, you should probably challenge yourself. Sit down and see if you can write a for loop. For example, writing a loop that goes from -5 to -10 in step sizes of 3, and see if you can write the loop. Practice like this is invaluable in learning a new language. Now we're going to move on to the Fibonacci sequence. This is not a math class. It is a series of videos to help you learn to program. So this explanation of the Fibonacci sequence and the generalized Fibonacci sequence is going to be as short as possible. This explanation is not going into great depth and is here to help you understand the code that is going to be generated. When talking about the Fibonacci sequence, the word "the" is part of the name, just like The Ohio State University. The Fibonacci sequence is also called the Fibonacci series, the Fibonacci numbers, and other variations. The Fibonacci sequence starts with two numbers, 0 and 1. All of the remaining values are calculated by adding the previous two numbers. The Fibonacci sequence is shown below. Mathematicians use F to represent the Fibonacci sequence. A generalized Fibonacci sequence is a list of numbers that follow the Fibonacci rules, but do not start with 0 and 1. A generalized Fibonacci sequence starts with two numbers, such as 2 and 4. All of the remaining values are calculated by adding the previous two numbers. A generalized Fibonacci sequence starting with 2 and 4 is shown below. Mathematicians use G to represent a generalized Fibonacci sequence. There are many online calculators for Fibonacci sequences. Two are listed below. You may wish to review them if you are interested. I've updated the second group box. It has two text boxes, one for value 1 and one for value 2. These will be the two starting values for our generalized Fibonacci sequence. Value 1 will be a number between 0 and 10, and value 2 will be a number between 1 and 10. There's also a rule that will say value 2 must be greater than or equal to value 1. There's also an Allow Negatives checkbox. When this checkbox is checked, the range on value 1 and the range on value 2 will be extended to -10 to +10. There are also three radio buttons. These radio buttons determine how many values will be printed to the text box. The radio button for 10 has been selected as the default by changing the checked property to be true. The rules for this general Fibonacci sequence are shown in the comments. The rules for this generalized Fibonacci sequence are in the comments. First, we're going to start with a try-catch because we're going to be reading a value in from the screen. We have to use the try-catch to eliminate errors such as a person typing in the letter A for a number. There are two ways that we can use the try-catch. We can either end the subroutine if they enter a bad value, or we can use two try-catches, one for each of the values. If the person enters a bad value, we can load a default instead. Up to this point, this is how we've been using the try-catch. We put all of our code in the try, and if anything goes wrong, we jump to the catch, print out an error message, and end the subroutine. But I want to introduce you to a different way of using the try-catch. Here is the updated code. I started out by clearing the text box by setting it to nothing. All of the remaining print statements use append text. That allows me to print more than one error message to the text box if I need to. The first try-catch reads in the first value. If the first value is invalid, the catch takes over. An error message is printed to the text box, the first value is set to 0, and then the input text box is also set to 0. This lets the user know their value has been altered. The second text box does a similar task. It reads in the second value. If there's an error, the catch takes over. An error message is printed. The second value is set to a default value of 1, and the input text box for the second value is also set to 1, so the user knows the value has been updated. Let's test this code. I'll start by entering two valid values. Nothing happens because the code hasn't been written yet. Let's enter a bad value. As you can see, when a bad value was entered, an error message came up on the text box, and the value was updated on the input text box to a default value of 0. Now let's try running the program with two bad values. When two bad values were entered, two error messages came up, and both values were updated. The advantage of using the try-catch in this manner allows the computer program to continue to run even if bad values are entered. However, you can use either method. It just depends on what you want the program to do. At this point, we are guaranteed that we have two integers, but that does not mean they are valid integers. Our program has constraints on the integers that we can use, so we need to further filter the data. This is often done with an if block, and each if statement in the if block checks for one type of bad input. The code that runs if everything is valid is inside of an else statement. I will start by looking at the checkbox. This is important because the checkbox changes what is considered valid data. Now I'm going to nest an if block in the checkbox if statement. Each if statement in this block will correspond to one rule. If any of these statements are true, an error message will be printed out and the rest of the if block will be skipped. If none of them are true, the else will execute, and that's where the code will be written. Now it's time to write the code for the Fibonacci sequence inside the else statement. We're going to need a variable that will tell us how many times the loop's going to run. This integer, int end of loop, will be used as the stopping condition for our for loop. The variable will get its value from the radio buttons. The first two values were read in from the screen, so they don't need to be calculated. They can just be printed to the output text box. The first print statement is a textbox.text. This will erase everything on the text box before the text is written. All of the following print statements will be append text because we don't want those to erase the previous information. The remaining values need to be calculated inside of a for loop. Because the first two values have already been printed to the screen, our loop can start at 3. The equation that we're going to use to generate the Fibonacci sequence is inside of a loop. That's because the same equation is going to be used over and over and over again. And when a job is being repeated, it's usually inside of a loop. The equation to generate the next Fibonacci value is third equals second plus first. In order to do a sequence like this, all the values on the right side of the equation need to have been read in or calculated before we get to the loop. The left side of the equation is where the new answer is going to be placed. Now we can print third to the screen. The print statement is going to print the word value, followed by the loop index I, followed by a colon, followed by the calculated value. I will change with every pass of the loop. However, int third value won't. Assume int second value is 3 and int first value is 2. Then the equation int third value equals int second value plus int first value will generate the number 5. If this equation is inside of a loop, the number 5 would be generated every time the loop runs, as shown in the table below. This is because int second value and int first value are not changing. The program needs to update the values inside the loop so the sequence can progress. What should happen when the loop runs is shown in the table below. Please note that the values are shifting every time. Every time int third value is calculated in the loop, all of the values need to shift one place. The order you shift the values matters. If these two lines were reversed, int third value would overwrite int second value, and the original int second value is lost. This would cause the next line to pass int third value onto int first value as well. The resulting error is shown in the table below. The correct shifting code is shown below. Now that the values are updating, this will generate the correct Fibonacci sequence. Before I demonstrate the working program, I'm going to finish the code behind the checkbox when it's checked. The code is nearly identical to this code. The only thing that's really changing is the error checking at the beginning of the if statement. The code inside of the else is exactly the same. Let's run the code with the checkbox unchecked. First, we'll test the error checking. The try-catch changed the letter W to the default value of 0 and ran the program. Now let's run this with bad integer values. As expected, the error code for the first value being out of range is displayed. And the second error code also works. And the third error code also works. Now we'll test the radio buttons. 10 values were generated, and the sequence is correct, because 2 plus 6 is 8, and 6 plus 8 is 14, and so on. Let's see what happens when we choose 20 values. As expected, we get all 20 values. Now, let's try 30 values. Again, the program is working. Now let's verify the program using the Allow Negatives checkbox. I've adjusted the code on the screen so you can see what happens when the checkbox is true. Again, we're going to check the error messages first. Error message 1 works. Error message 2 is working. Error message 3 is working. And error message 4 is working. Now we're going to test the radio buttons. "10 values works. 20 values works. And 30 values works." In review, for loops are used when the loop is going to run a fixed number of times. An example of a for loop is shown below. In this example, the loop index is the variable I, and it controls the loop. Historically, the loop index is I, J, K, L, M, and N, but it can be any variable. The loop index can be a number with or without a decimal point. The starting value follows the equal sign. In this example, it is 1. However, a starting value can be a number or a variable. It is where the loop index starts counting. After the loop index is assigned a starting value, it is checked against the stopping condition before the loop starts to run. Therefore, a for loop may not run. The loop index is compared to the stopping condition. In this example, it is a variable int number. However, the stopping condition can be a number or a variable. If the loop is counting up, the loop will run as long as the index is less than or equal to the stop value. If the loop is counting down, the loop will run as long as the index is greater than or equal to the stop value. The step size in this example is 1, but it could be a numeric value or a variable. If the step size is positive, the loop counts up. If the step size is negative, the loop counts down. When loops are introduced, it is common for textbooks and teachers to have the students write a Fibonacci sequence. Technically, there are 2 variations. The Fibonacci sequence starts with 0 and 1. The next value in the sequence is the sum of the previous 2 values. A generalized Fibonacci sequence starts with any 2 numbers. The next value in the sequence is the sum of the previous 2 values. When values are read into a program to perform calculations, it is common to perform error checking and filter unwanted data. The code is often put in the try of a try-catch. This will prevent the program from crashing if a letter is entered for a number or a similar error that will throw an exception. Once the values have been read in, the data is usually filtered with an if block. Each if statement in the if block looks for one type of invalid data, such as a value that is too large, a value that is too small, or values that are out of order. If the try-catch is not tripped, and all of the if statements are false, then the entered data is valid. The code is then written inside of the else statement. In the example of the Fibonacci sequence, a loop is needed to generate the remaining values. This is true for most programs that are generating a sequence of numbers, such as IRA estimates, home loan payment schedules, population growth estimates, and many more. Before the loop runs, the program must have all the values it needs to calculate the sequence. I usually tell my students that this is collecting the raw materials. You know if you have all of the needed values when you have all of the values to create the loop and you have all of the values on the right-hand side of all of the equal signs. This example uses discrete variables. That means there are only a few variables and they will need to be reused. When the values are generated in the loop, the old values are erased. This is different when an array is used to generate the list. Arrays will be covered in an upcoming video. To continue generating the values in the list, the values must shift position. In the case of the Fibonacci sequence, the shifting is shown below. If you find these videos useful, please like and subscribe. It is the only way I can continue to make these videos.